So what's simple harmonic motion? Simple harmonic motion is basically a special type of oscillation. Oscillation being any repeated movement that's cyclical over time that continues. Uh, Simple harmonic motion happens in pendulums or swings at smaller angles. Happens on masses on springs. It models their movement as well as, and also it does that for floating objects. So, like any oscillation, this has an equilibrium point, and so this particle has displacement from there. It also has acceleration and velocity in this case. So the acceleration, particle having mass, creates a force, and this force is a restorative force back to its equilibrium point. So in the case of a pendulum or a swing, that force is gravity bringing it back to that lowest point before anything happened. For a spring, it's the spring force bringing it back to where it started, and for floating objects, it's going to be upthrust and gravity. So the special thing about simple harmonic motion is that it follows this definition where acceleration is proportional to displacement in the negative direction because there's a restorative force, and it's proportional by the square of this quantity called angular frequency, which is represented by omega, angular frequency. So this quantity, angular frequency, it's not angular velocity. They're different things. They measure completely different things, even though they sound like they would be the same thing. It's also measured in radians per second like angular velocity is. But this quantity is related to the frequency and the period of the oscillation. And it's not W, it's omega. So for simple harmonic motion, there are equations that model the movement of whatever particle you're measuring. Since we have this formula A equals negative omega squared x, we can figure it out since we know that acceleration is basically the second derivative of whatever formula models its displacement with respect to time. So what's x? We can find this out using a differential equation. But basically, to simplify it, if we do whatever math that is, we figure out that x is a cosine omega t, where a is the amplitude, cosine is cosine, omega is the angular frequency, and t is time, measured in whatever. So from that, if we take the second derivative, we know that a is negative a omega squared cosine omega t, and v equals negative a omega sine squared omega t. And that's how we get these formulas. Okay, so for simple harmonic motion, since there is a force and a moving mass, there's going to be some energy involved with this. So let's take the example of some mass moving on a spring. And if it's displaced x away from whatever equilibrium point it has, it'll have some sort of acceleration back towards its equilibrium point. And we know that its force is negative kx from Hooke's law, where k is the spring constant measured in newtons per centimeter or whatever. So the average force of the particle when it's moving from that equilibrium point and to that maximum displacement, whatever that is, say the amplitude, would be negative kx over 2. And to find the work, it moves x distance, whatever you're measuring at, so you get negative kx squared over 2, and its potential energy would be the negative of that. So potential energy based on the spring would be kx squared over 2. And for kinetic energy, we know that from the formula we've learned in kinematics or whatever, ek equals half mv squared, since the particle is moving after all. So let's assume this whole simple harmonic motion thing is happening in a closed system. So no energy is dissipated through friction or by air resistance or any sort of opposing forces. So our total energy is going to be the sum of our potential energy and our kinetic energy. We can sub in the formulas, so we know that total energy is equal to kx squared over 2 plus mv squared over 2. And since this is a closed system and no energy is lost or gained, this is going to be a constant. So as the particle moves on the spring or whatnot, it's not gonna, total energy is gonna stay the same. Nothing's gonna change in that, like, in that respect. So what does this look like when we graph it as it moves from the amplitude from the negative end to the positive end, depending on however you define it? So if we mark that and our equilibrium point as 0 right in the middle, as so, we can start graphing this. As said before, our total energy is constant, so it's going to be a straight line. And so what happens to potential? What happens to kinetic energy? So everything we've discussed so far has applied basically to a perfect world. So everything's essentially a closed system. No energy has been added to it. No energy has been lost through friction or air resistance or anything. So now let's take this into the real world, where there are going to be opposing forces to the particle undergoing subharmonic motion. So when there are opposing forces, that causes damping, where the energy slowly dissipates over time due to having the force there. So the amplitude also decreases over time since they're both related to one another, and that's damping. And the opposite can happen with resonance, where the force is not opposing the movement of the particle but helping it. So it starts out with a smaller amplitude and slowly builds up over time, gaining energy. The amplitude gets higher and bigger. So that's resonance. Again, they're pretty much opposites from one another. So yeah. So let's look at damping in a bit more detail. Again, we know that damping is when that particle, that system, loses energy over time due to some opposing force. So basically, it happens in the real world. And let's take the analogy of some kid on a swing in a playground. So the kid's happy. He's swinging and his dad's pushing him or something. So this model is a pendulum or swing. It follows simple harmonic motion to a degree. So he has some sort of amplitude. That's the height that he manages to reach at by himself, let's say. And let's say he's reached that thing and he's falling back down to that equilibrium point. So there's some sort of acceleration there due to gravity. And let's say his dad decides to come and just push him at that point. So that's not going to do much. He's opposing that force, and the acceleration, cancels out. The forces cancel out. It's not helping. So the kid's sad, and the dad's just a mean dad. I don't know why, but yeah. So let's look at resonance in more detail like we did with damping. So again, resonance is when there's a force helping the movement of the particle. So it gains energy and its amplitude goes bigger over time, as you can see from the graph over there. Let's use the same swing example where you have some kid on a swing. Its equilibrium point is going to be at where the swing sat before anyone got on it. And he's swinging, and this time his dad isn't going to be a mean guy. He's going to wait for the kid to get to his top, its apex of his swing before pushing him. So without his dad there in the first place, he's going to have some force bringing him back to equilibrium point. And with his dad there, it's adding even more force. So that's giving him more energy, and it's helping the resonance, so he can go even higher. And if we know that continues, you go even higher and higher, so the kid's going to get happy. And the further away the kid is from an equilibrium point when his dad pushes him, that's going to give him more force. If he's at the amplitude of whatever swing he was at and his dad pushes him there, he's going to go even higher than he did if he wasn't there, because that's when the restorative force is greatest.